Hello students. Today in this video I would like to discuss a very interesting method to solve differential equation. Now before we get there, I would like to remind you what we already have seen so far in this chapter. We have seen two special type of differential equation, namely separable DE and first order linear DE. We know general technique to solve both of them, and we have solved series of examples involving them. In the last lecture, we have seen one very interesting application of both of this type of differential equation. We talked about continuous compounding, continuous deposit, and continuous withdrawal. We've seen at least two or three examples related to both applications. So now the question is, why do we need new method? Let me explain you this with one very interesting and straightforward example. Suppose I give you this differential equation. Let's say I give you dy by dx equal to x plus y square. Very simple looking differential equation. Alright? The first thing that I want you to notice is that this differential equation is not a separable DE. Alright, so this differential equation is not separable. Why is that? Because we can't separate x and y from each other using the equality. Alright, I can't see the right hand side in terms of function of x times function of y. Okay, is it a first order linear differential equation? Answer is no. Remember what I said about first order linear differential equation? It's a differential equation that is linear in y and its derivative. So the highest power of dy by dx, you want it to be equal to 1, and the highest power of y, you want it to be equal to 1 as well, right? Unfortunately, that is not the case here, so this is not a first order linear DE as well. Okay, so this is the differential equation that looks very simple. Unfortunately, we don't know how to solve it. Okay, all right, so the question is, what should we do here? What should we do in this type of case? Well, we have one very interesting method that can be used to solve any first order differential equation. All right, let's try to see this method. It's one very simple and straightforward result. It's called Euler's method. Let me give you the statement first. Once we have a statement, I'll show you maybe one or two quick examples, and that will be the end of the story for today. Okay, so here is the statement. Let y equal to g of x be a solution of an initial value problem dy by dx equal to function of x and y with initial condition y at x naught equal to y naught for the region or on the region that consists of all x values between initial x value and some xn. All right, and let xi plus 1 be obtained by simply adding h to the previous x value. Let me tell you what x is, where h is xn minus x0 divided by n. All right, we have one more unknown thing here. Xn and x0 is something that we know already. N is something that we don't. Let me tell you what n is. N is number of numerical solution that we are looking for. So let xi plus 1 be xi plus h, where h value is xn minus x0 over n, where n is really the total number of solution, numerical solution that we are attempting to calculate. In such case, I can calculate numerical solution, I plus 1th numerical solution, using the following formula. It is yi plus h times function evaluated at xi yi. Alright. So this is the formula to compute I plus 1th solution. Think about it. What do we need to compute I plus 1th solution? I need yi, I need xi, and I need h. Alright. H will be a constant numerical value. Yi is the previous solution, ith solution, and xi is also something that we can compute. Alright. So if you know these three values, then you can produce I plus 1th solution. This particular solution method is called iterative solution. The reason is you are using the previous solution to get the new solution, to get the next solution. Alright. Such a method is called iterative solution method. Okay, so we can calculate I plus 1 solution. If we keep doing that, then what we are going to get is following. Our yi plus 1 will be equivalent to the solution g at xi plus 1. Alright. Again, this is an approximation technique. It may or may not give you exact solution. The more partition you consider, more closer you will be to the exact solution. Alright. So solution should be more accurate if you consider splitting the region of interest into many subintervals. So if you calculate like 100 iterative solutions on a small interval, let's say 0 to 1, then you will be staying very close to the actual solution, then considering 10 subinterval, 10 parts of interval 0 to 1, or 5 parts of interval 0 to 1. Alright. So finer partition will keep you very close to the actual solution. So as I said, this very straightforward result is called Euler's method, and it is a technique to find out the solution of any first order differential equation. As I said, good news is this method can be used for differential equations that are neither separable nor first order linear. Right? So after this lecture, you will have an idea on how to solve any type of differential equation, at least numerically. Okay. All right. Let's try to see an example. Okay. I'm going to start this discussion with a very simple example. Would like to show you one clear example to show you to demonstrate that what this method really does. Okay. So here is a problem in 3 parts. Let's say solve IVP dy by dx equal to 2x with initial condition y at 0 equal to, let's say, 2. Okay. Number 2, compute, let's say y at 0. Okay. Number 2, find, or let's say evaluate the solution at x equal to 0.2, 0.4, 0.6, 0.8 and 1. Alright, so I want you to evaluate your solution at these 5 different inputs. Alright, so if we know the solution, in order to evaluate solution at those points, just replace x by those values and we will get a numerical value for our solution at those particular inputs. Okay, and then part C, use the Euler's method to approximate the solution of dy by dx equal to 2x with y at 0 equal to 2 on the interval 0 to 1 with n equal to 5. Alright, so what I want you guys to do is find out first 5 approximated solution of this differential equation on the interval 0 to 1 only. Okay, meaning divide interval 0 to 1 into 5 segment of equal length, and that equal length will be our each. Okay, anyways, we know how to answer the first two questions, so let's try to answer those first two questions very quickly. So here is the solution for part A. It's a very simple separable DE. Alright, let's separate the variables. Once the separation is done, need to integrate both sides with respective variables. Antiderivative of 1 with respect to y is y. Antiderivative of 2x with respect to x is x squared, and then you throw a constant of integration there. Okay, get y equal to x squared plus c. Because initial condition is given, let's use it. When x is 0, corresponding y value is 2. Let's plug it in. 2 equal to 1 0 square plus c, and looks like we get c equal to 2. So out of infinite choices, this is the one that satisfy my data. Alright, so I would go ahead and throw it into the general solution. I get particular solution, which is y equal to x squared plus 2. Alright, so that is our particular solution. Now I can answer number 2. Alright, as I said, number 2 is just a plain computation. This is my solution function g of x. Okay, I want to evaluate this g at 0.2. You can also write it like this, y at 0.2. Alright, plug x equal to 0.2, 0.2 square plus 2, and this is gonna give me 0.04 plus 2. This is 2.04. Nice. Calculate the solution at 0.4, or calculate y at 0.4. I get 0.4 square plus 2. I get 0.16 plus 2, 2.16. G at 0.6 or y at 0.6. This is gonna be 0.6 square plus 2. 0.6 square is 0.36. 2.36. Evaluate your solution at 0.8. Again, fair deal. 0.8 square plus 2. 0.8 square is 0.64. And if you add 2 to it, you get 2.64. Okay, and finally evaluate your solution at 1. Okay, this is going to be 1 square plus 2, 1 plus 2, and that's going to be 3. Alright, these are the exact value of the solution at those inputs: 0.2, 0.4, 0.6, 0.8 and 1. These are exact value of the solution at those inputs. want you to keep them in mind. Now, as I said, we are trying to now answer the main question, all right, how to use Euler's method in this problem. Let's use it. Let's see it. Okay, so here is our differential equation. Dy by dx equal to 2x, y at 0 equal to 2, and I already mentioned that I'm looking for the solution on the interval 0 to 1, where it starts with that initial point, right? And you want n to be 5. Okay, so first and foremost you will have to find out your h value. Okay, so let's recall. Compute h. H is going to be, this is your x0, this is your xn. It is xn minus x0 divided by n. Okay, let's throw the values in. 1 minus 0 divided by 5. This is 1 over 5, and 1 over 5 is 0.2. Yeah, all right. So my h value is not going to change, it will stay constant. Okay, all right. Now this y0, it's going to be the initial condition, right? I'm going to start from here. Start with the initial data. x0 is 0, y0 is 2, and h is 0.2. I'm ready to produce the first numerical solution using the formula. Okay, let's do it. What is the formula? It says first solution is zeroth solution plus h times f of x0 y0. Now remember, what is f of xy? F of xy is our right side of our differential equation. Okay, f of xy is really the right side of the differential equation. It's 2x currently. Okay, so let's throw the values in and it will tell us what else is needed. I'm gonna replace y0 by 2, h is 0.2, and f of 0 2. All right, think about it. How do I evaluate f at 0 2? Well, f of xy is 2x. F at 0 2 can be evaluated by simply replacing x by 0, y by 2 in here. Let's do that. Replace x by 0. There is no y there, so it's just going to give me 0. So this part right here is 0. 2 plus 0.2 times 0, and I get 2. This is the first approximated solution of my differential equation. Again, this is the first approximated solution of my differential equation. Okay, to calculate the second approximated solution, I need y1, I need x1. All right, y1 is already there, I need x1. How do I get x1? Well, simple. In the previous x value, add h. All right, previous x value was 0. I'm adding h value to it, get 0.2. So my updated x value is 0.2 now, updated y value is 2. Okay, and h, it stays the same. Okay, I have all these three things available. I am ready to calculate the second solution. Let's do that. y2 equal to y1 plus h times f of x1 y1. Again, you see, I copy the same formula, but now with x1 and y1. So my first solution will give me the second solution. Second one, I will use it for third, fourth, and fifth, and that's how we calculate numerical solution. Okay, so let's plug the values in. My y1 is 2, h is 0.2, and I need function evaluated at 0.2 comma 2, right? So I need f at 0.2 comma 2. Our function is 2x, so 2 times 0.2 looks like 0.4 is what I'm gonna get. So this part is 0.4. So 2 plus 0.2 times 0.4. Let's multiply them. 2 plus 0.08, and this is going to be 2.08. So this is the second approximated solution. If you want to calculate the third approximated solution, you need y2, x2 and h. Let's do that. We already know the technique now. y2 is 2.08. x2 is going to be previous x value plus h, right? Previous x value plus h. Look, x1 was 0.2 already, plus h is going to make it 0.4. H value stays the same. Okay, ready to calculate the third solution. y3 is y2 plus h times f at x2 y2. Throw the values in. 2.08 plus 0.2 times f evaluated at 0.4 comma 2.08. Right, gonna evaluate this function on a side. F at 0.4 comma 2.08 is going to be 2 times 0.4, and this is 0.8. Okay, I'm ready to plug that value in here. 2.08 plus 0.2 times 0.8. 0.2 times 0.8 is 0.16, and they adds up to 2.24. This is the third approximated solution. Alright, remember how many solutions do I need? I need first 5. Okay, let's compute the remaining 2. Okay, so let me copy this data. y3, third solution was 2.24. I need x4 as well, sorry, x3 as well. X3 will be x2 plus h. What is x2? It is 0.4. You add 0.2 to it, it's 0.6, and h stays the same. Okay, let's calculate y4. y4 is y3 plus h times f at x3 y3. By the way, there is no need to write down this formula over and over. If you want, you can write down the values directly. Okay, since this is the first example, I'm going to write down every single step here. Alright, x3 is 0.6, y3 2.24. Evaluate this function on a side. F at 0.6, 2.24. This is 2x, right? So 2 times x is 0.12. Okay, I'm ready to plug those values in. 2.24 plus 0.2 multiplied by 0.12. Looks like we get 2.24 plus 0.24. The sum will be 2.48. This is our fourth approximated solution. Okay, and then let's compute the fifth one too, just to finish this example. I got y4 equal to 2.48. x4 is going to be x3 plus h, and x3 was 0.6, so x4 is going to be 0.8, and then h is 0.2. Okay, y5, it's going to be y4 plus h times f at x4 y4. Throw the numbers in. Y4 is 2.48. This is 0.2. F of 0.8 comma 2.48. Evaluation of my function at 0.8 comma 2.48. Fairly simple. Just plug those x and y value in your function. You get 0.16. So I get 2.48 plus 0.2 times 0.16. This is 2.48 plus 0.32. It's going to be 2.80. So I got 5 approximated solution, and we have 5 exact solutions. All right. Let me just make a very small table just to demonstrate that how far we are. All right. So here is the exact solution. Here is approximation. Remember, we calculated values of our solution at 0.2, 0.4, 0.8, 0.6, 0.8 and 1.0, right? These were the numbers. The first solution, exact solution was 2.04. Alright, the second exact solution was 2.16. This was 2.36, 2.64 and then 3, right? And then approximated solutions, we got the first solution 2. Want you to check that they are off by like 2 decimal places, right? Okay. The second solution was 2.08. The third one was 2.24. Fourth one was 2.48 and third one was 2.80. Alright. So that's the exact solution. These are the approximation using Euler's method. Again, what I mentioned earlier was that if you divide that small interval into more partition, so instead of 5 partition, if I have divided it into 10 pieces or 20 pieces, 40 pieces, then 40 pieces would keep me very close to the exact answer. The more finer partition you consider, the more accurate your answer will be. Alright. So Euler's method, good thing about it is you don't need to know the exact solution. Alright. As far as you are moving very closely, very slowly, as far as your h value is small enough, it's kind of giving you the guarantee that you will be staying close to the original solution. Right? So this is the main idea of this this entire lecture. Let me give you one more example to end this story. Here is the second example. Let's say let's consider the same differential equation that I used earlier. Use Euler's method to solve this differential equation dy by dx equal to x plus y square with initial data y at 1 equal to 1 on the interval 1 to 1.5. I want you to 1 to 2.5. I want you to notice here that that interval starts with initial x value, right, ends at 2.5 with h equal to 0.5. Okay, now this example looks slightly different than the first example. In the first example, I told you how many solutions I am looking for, and based on that you calculated h value, right? Here I am giving you h value. You have to figure out how many solution do we need. Alright? In order to do that, you will have to use the same formula. This is your x naught, this is your xn. Okay? So, here is the solution. First and foremost, understand how many solution you need here. Okay? So, let's do that. We first compute n. Remember, h and n are related like this. H is xn minus x0 divided by n. Alright, throw the values in. H is 0.5. This is 2.5 minus 1 divided by n. You see, there is only one unknown. Solve it for n. I get 0.5 equal to 1.5 divided by n. So my n is going to be 1.5 divided by 0.5, and this is 3. I only need the first 3 solutions. Okay, again, I only need the first 3 solutions. Let's quickly calculate them. Okay, so to calculate the first solution, I need x0, y0, and h. Let's write them down. x0 is 1, y0 is 1 as well, yeah, and then h is 0.5. My first solution is going to be y0 plus h times f at x0, y0. Throw the values in. Y0 is 1, h is 0.5, and then f at 1, 1. Okay, now remember, this is my f of xy, the right side of my differential equation. I need to calculate f at 1, 1. Replace x by 1, y by 1. Looks like we get 2. Okay, so this block is just 2. I get 1 plus 0.5 times 2. Well, 0.5 times 2 is just 1. I get my first iterated solution, which is 2. I need the second one, so let's use the first iterated solution. I need to update the value of x. Alright, it's really x0 plus h. What was x0? x0 was 1 plus 0.5. I get 1.5, and h stays the same. It's gonna be 0.5. We are ready to throw these values in. Okay, so I get y2 equal to y1 plus h times f at x1, y1. Throw the values in. Y1 is going to be 2. This is 0.5. F at x1 is 1.5, and y1 is 2. Alright, let's obtain this value. Looks like we get 2 plus 0.5 multiplied by, let's obtain this, 1.52.